looking at the chain rules, we're just going to do the same thing. We're going to let the inside function be represented by u. Then the derivative of that, or excuse me, the integral of that derivative, let me pull this down here a little bit. The integral of that derivative, then, we could actually put a u in here and then have a du dx show up here. Okay, and we come down to the outside function of the inside, so capital F with the inside of the function u. If you put g of x in there, we got the same thing as this. Okay. Yeah, that's okay, but let's look a little bit deeper into this. Here's our theorem. Let's just take a look at it a little bit at a time. So the antidifferentiation of a composite function. Find the antiderivative when you're given a composite function derivative. Let g be a function. Now, whose range? When we talk about a range, we're talking about the outputs, possible values. So the outputs of g are in the interval I, and f is a function that's continuous on that same interval. Then if the inside function is differentiable and the, I'm wondering if maybe we have this should be capital F. And f is an antiderivative of, in other words, okay, let me highlight some things here, because here's where we go back to our cap F and small case f. Small case f in this case is the integrand. Okay, so the derivative is a function that's continuous on the same interval as the inside function. Then the outside function is an antiderivative of the integrand. Well, what does that mean? Then, okay, g of x is the inside function. We let u be g of x. The derivative, now, okay, let's pull this apart. Look at this. We have said, and some of the purists will say, and when we first talk about derivatives, you can't pull apart du dx. Well, we kind of do. They kind of do represent some things that we can look at individually. But look what happens here. That says du. That's the derivative. That's the differential, I should say, of u. If I look at du dx is the same thing as g prime of x. Do you see where this comes from? They're multiplying the differential of x to both sides. Okay, so we see where that comes from. And the integrand of f of u du is the antiderivative. So this is the original function with respect to u. Then this whole thing can be written in terms of x, and that's what we're headed for, is putting it back in terms of x. Now, I'm going to give you a process. It helps if you see patterns, but patterns only come after you do 100 of these things, or 25 maybe. But we don't always have the time, or we don't always take the time to search out problems so we can see the patterns, and the patterns can change a little bit. So I'm not going to ask you to look at patterns. I'm going to ask you to just follow a process I'm going to give you, and hopefully through that process we'll get the answers. Okay, so here we go. Again, this may or may not be number 16. My notes are the same as when the old edition, and then we just had that last semester, and the numbers might change. Okay, find the indefinite integral of this. In other words, find the function for which this is the derivative. Now, at this point, how much do I expect you to understand of this? At this point, I would hope by now you understand this is a derivative. Okay, so if right now you see that and you understand that, you're on your way. You've got what we need to see right now. If you look at this, this is let's see, you've got a product and you've got a composite function in here, and we can't use our very simple little rule we have from 5.1. So here we go. Do you like green or should I go back to blue? Green's fine. Okay. Sometimes green doesn't show up as dark, so I just wanted to know. Let's let u equal something in here. Now, the question is, what do I let it equal? That's going to be the first thing you have to think about. Well, I would say, can you identify an inside function of this integrand? And if I do that, I would have t to the fourth. Oops, I didn't say let u equal. So let's go back and put the u in. Let u equal t to the fourth plus 5. If u has that value, can you take the derivative with respect to t of that? Yeah, 4t. Okay. And if we have this, can we write this as du equals, oops, 4t cubed, sorry. Can we write that as du equals, and we can, be 4t cubed dt? Now, what I am wanting to do, you see this dt up here, this differential t, and you see this t cubed? What I'm going to do, I'm going to rearrange. It's multiplication. Multiplication is commutative. So I'm going to rearrange. I'm going to make this t to the fourth plus 5 to the 1/2 power. And I'm going to put together now t cubed dt. What I would like to do, let's go back here. What I would like to do is to be able to write then my integrand in terms of u with the differential u, because that's going to make it a simpler problem. So let's see if we can accomplish that. Du could replace this whole thing. The problem is, I've got 4 here, and I don't have 4 up here. Now, there's various ways that people can instruct, but this is the way that seems to make it easier for all of us. What if I divide both sides by 4? Okay? Divide both sides by 4. Now, I've got t cubed dt and t cubed dt. Could I make a substitution and put in its place 1/4 du? Yeah, I could do that. So now, let's do this. Let's make a substitution. And we're going to do this a couple of times. This is substitution number 1. And let's write this whole problem now as the integral of, and instead of t to the fourth plus 5 to the 1/2, I could write it as u to the 1/2, okay. And instead of t cubed dt, I could write it as 1/4 du. Now, what do you know about a scalar in a problem? You know, I could write this as 1/4 u to the 1/2 du. I could also, because we had a rule back in 5.1 that says if you have a scalar, you can actually pull it out in front. That happens with a lot of our math work. Is this an easier problem to work now? Much easier. Okay. How did we get there? Well, these are the patterns you look for. And the pattern I'm looking for is, you can't always go for the most complicated part of it, but I'm looking for an inside function. Something that I can rewrite to make it look really simple. And so if I let this be u, then I've got u to the 1/2 instead of the square root of this. And so if I let u be that, I take its derivative, and I come down and I multiply both sides by the differential t. And what I'm aiming for is I want to replace this piece with something in terms of u, du. And I can do that if I divide both sides by 4, and I've got this really nice simple problem now. So now if I integrate this, I have 1/4. Now we're going to keep it in terms of u just for a moment here. So I have it as 1/4, or in terms of u. So what do I do to integrate u to the 1/2? Let's see, the first thing we do is add 1 to the exponent and divide by the new exponent plus c. Now, what have I just now created? I took the integral of that, so now this now is actually the function in terms of u. Okay, so I've got, let's see, 1/4, and this becomes u to the 3/2 divided by 3/2 plus c. Divide by a fraction is the same as to multiply by the reciprocal. So I have 1/4 times 2/3 u to the 3/2. Now here's where you have to kind of allow yourself to think more, think beyond the fact that if I have a c, I now have 1/4 c. What does c represent? Any constant, right? A constant. It can be any value at all. So if I take any value and divide by 4, do I still have just any value? Yeah. This is not what you want to go home and show your siblings or cousins or whatever who's in Algebra 1 and say, look what we can do. We can take 1/4 of c and just get c again. Yeah, you don't want to tell them that, okay? But we understand that c represents just any value, and so 1/4 of any value is still any value. Okay. So I can, change this to be, what is this, 1/6 u to the 3/2 plus c, and that's f of u. Now, is that the problem we started with? No. We started with the problem that had an input variable of t. We've got to go back. That's the second substitution then that we do. So substitution number 2. We're going to take f of t, and we're going to, actually, that's not correct. What does u represent? T to the 4th plus 5, and we're going to have to use that and then I'll just say f of t equals this. Again, we're taking some liberties with the algebra we've always known. Okay, I could change this to g if I wanted to, if that helps, if you want to do that. Okay, now, how can I test to know if this function creates this derivative? Take the derivative. Yeah, just take the derivative of it. Now, because I want you to have a way of checking a lot of problems, and taking the derivative is one of them, and be prepared to explain that, use your Inspire So to check your check, if nothing else. Go to the, go to a calculation page. If you go to Menu, go to Calculus. Down here at number 3 is Integral. Have I shown this for 5.1? Did I show this to you? Okay. So now, don't worry about these upper and lower bounds, because we're going to fill those in later. Right now, we're doing indefinite integrals. We're not doing definite ones. And you'll see what the difference is. So just tab over. And in the integrand, we're going to put in, and you can put a t in. You don't have to put x in. And if we're going to graph it, we'd want to put x in. But I'm going to go ahead and put a t in there. So what do we have? T cubed. T to the 4th plus 5. Okay. So t cubed. And then the square root. T to the 4th. Plus 5. And what am I going to have to do with the differential? Yeah, be sure they match. And let's see if we get the same answer. Now, what's missing from this answer? What? Plus C. I think you said T. Plus C. Yeah, so make sure you have that. Okay,